It is a section 3.2. In this section, we'll consider some properties of determinants, particularly the determinant change under elementary row operations. Then we'll define the determinant function and consider its linearity property. See this theorem. A is an m by n square matrix. B is obtained from A by a replacement. Then determinant of B is the same as determinant A. For example, here A is 1, 3, 2, 1, so that its determinant is 1 minus x, so that is minus 5. Determinant of A is minus 5, and now its echelon form is made twice. First row is subtracted to make it 0, and that becomes minus 5. Now the determinant of B is minus 5 minus 0, so it is a minus 5, unchanged. So this replacement is not changing the determinant. How about interchange? When interchange is applied to get B from A, then determinant B is negation of determinant of A. Okay, the same metric and row interchange is made. And if we try to get determinant, 6 minus 1, AD minus BC, so it is a 5. It is a negation of the determinant of A. How about scaling? And one row of A is multiplied by K, non-zero. Then, now the determinant of the new metric is K times of determinant of A. Here, now for this example, K is chosen minus 2. So the second row is multiplied by minus 2. Now we'll try to get from here determinant of B, determinant of B, that is, now minus 2 and minus 12, so that minus 12, which is 10. This 10 is the same as the determinant of A and times minus 2. Minus 2, that is K, times determinant minus 5, which is determinant of A. Row scaling makes the determinant the same A scaled. But for this one, you should not be confused along with here metric multiplication by a scalar. For example, minus 2 of A. In this case, we multiply minus 2 for whole metric. Then here from this metric, we have here now minus 2, minus 6, and the second row minus 4, minus 2. Okay. Then from here, the determinant is AD 4 minus 24. So that will be minus 20. That can be written in this way. Here, minus 2 squared times minus 5. Minus 5 is determinant of A. Minus 2 is K squared. So this multiplication can be interpreted in this way. First, we multiply minus 2 for the first row from A, and then again one more time of minus 2 multiplication to the second row, so that minus 2 is multiplied twice. So you put here minus 2 squared and times determinant of A. Okay. compute determinant of A when A is given in this way after applying a couple of steps of replacement operations. Okay, from A, we apply elementary row operations. Now let's try to make echelon form or toward the echelon form. So that 1, minus 4, and 2, 1 is the pivot now, and added, then it's 0, and that is minus 3, added, then it's 2. Twice added, then it's 0, twice added, again 0, twice added, then it will be minus 5. Okay, this is an echelon form of the metric, and this is a triangular metric. The determinant of triangular metric is product of the diagonal entries 1, minus 3, minus 5, multiplication will become 15. Right? So this techniques are much simpler than try to get the determinant directly from the metric. So you can use the elementary row operations and smartly to get a better computation. Okay. Here we have extension of invertible metric theorem. If A is invertible, square metric A is invertible, if and only if determinant A is non-zero. Okay. Here, determinant is a kind of the volume scaling factor. And once determinant of A is 0, then a non-zero vector will become 0. That means that the AX equals 0, the homogeneous system has non-trivial solution, which means A is not invertible. We start with a determinant AX 0 and we reach a non-invertible. So once also you may start from here to there, so that they are equivalent. So invertibility is the same as non-zero determinant. Okay, we have some more properties. A and B are n by n matrices. Here, transpose. Transpose is now row and column change, so that this first row becomes the first. Okay, first column becomes the first row, and second column becomes second row, or first row becomes first column. Either way, you can consider. Now, transpose, okay, determinant of transpose of A is same as determinant of A. For the same metric we considered earlier, the determinant A is minus 5. For that one, again, 1 minus x, so that determinant of A transpose is minus 5. Now, that is a property you'll use many times. That is now AB multiplication determinant is same as now multiple of each determinant. Okay, A is given here. Now B is given here. If you multiply AB, then you can reach that one. Only we know determinant of A is now minus 5. Right? How about this one? 2 minus 4. Okay, that is minus 2. How about this one? Determinant of AB is here 13 times 4 is 52 minus 6 times 7 is 42. So that must be 10. So here, minus 5 times minus 2 is the same as 10. Right? Okay. A is invertible. Then here, determinant of A inverse is same as 1 over determinant of A. Okay, that can be proved quite easily. Now, A transpose inverse of A is identity. So we apply determinant both sides. Then determinant of A inverse A is same as, by using this property, that will be same as determinant of A inverse times now determinant of A. Now determinant of identity is 1. Is identity is upper and lower triangular, and for those triangular matrices, the determinant is product of diagonal entries. Identity has all 1 along the diagonal, so that determinant is 1. Now from this equation you can get here determinant of A inverse is same as 1 over determinant of A quite easily. Suppose the sequence 5, 5 matrices A1, A2, A3 are related by following elementary row operations. Now find the determinant A when A3 is given in this way. Okay, so we can trace back the determinant of A starting from determinant starting from A3. Okay, this is echelon form and upper triangular matrix. So product of the diagonal entries will be the determinant. So it's 3 times 2, and now along with this negation and negation, so that the determinant of A3 is 6, right? Now A3 is obtained from A2 with an interchange, so that the determinant of A2 must be minus 6, because interchange will change the determinant with negative 1 factor, right? Now here, that is scaling, and from A1 to A2, we applied this scaling. So in third row is multiplied by 1 over 5. So if it is not multiplied this one, then the determinant will be 5 times larger. So here determinant of A1 is now minus 30. Okay. Now A1 is obtained from A with replacement operation, so that determinant A must be same as A1. Okay, so here determinant of A is 30, minus 30. Okay. Now here we'll consider linearity property of the determinant function. A is an m by m matrix, and we indicate the columns of A, A1, A2, A3, and AJ, the jth column, and AN. Now, from this one, we here now rewrite in this way. We consider jth column as a variable, so the A is written in this way. Now we define transformation from Rn to R by applying determinant, so that for the metric we try to get determinant. Now we may consider this one as a transformation and as a function of x. Okay, that is the determinant function. Once we define this determinant function, then quite easily you can prove that here Cx, if we put over there Cx, then C times of Tx, quite easily, because one column is multiplied by C, so that the determinant is now C times of original determinant. Earlier, we considered scaling in multiplication of k to a row. Now, for each column, if you try to multiply a constant, then determinant will be changed correspondingly along with the multiplication factor. So that's exactly this one. And now second one, to prove this one, you need a little bit of computation. However, here now, if x is replaced by two components, u and v, then you may try to get determinant with u and with v and separately, and you can add. That is exactly this one. So t of x is satisfying these two properties so that the determinant function defined in this way is a linear transformation. Okay, this property will be very useful in more advanced courses. We'll not deal with this one in detail in this class. Okay. Let's go to true or false problems. Okay, if the columns of A are linearly dependent, then determinant of A is 0. Yeah, must be 0, right? Once the columns of A are linearly dependent, that means that each column of A, some column may not have pivot position, which means that it's not invertible. If it is not invertible, then determinant of A equals 0. Right? Okay, so it is true. Now, determinant of A plus B is the same as determinant of A plus determinant of B. Is it true? No. For matrix multiplication, if the addition is changed by multiplication, is true. But for addition, is not true. But you should not be confused along with such the determinant function. Okay. If three row interchanges are made in succession, then the new determinant equals the original determinant. Okay, it's not true quite clearly. Each interchange will make the new determinant negation of the earlier one. So 30 times makes negation and come back to a positive and again go to negative. So the statement is false. The determinant of A is the product of the diagonal entries of A. Also, this is false. If A is a triangular matrix, then it is true. However, for general matrix, it is not true. If determinant of A is 0, then two rows or two columns are the same, or a row or a column is 0. Is it true? That one is false. In fact, if this one, two rows or two columns are the same, or one row or one column is 0, then this direction, the determinant must be 0. However, even though these two is not satisfied, determinant A can be 0. And for example, just the columns are linearly dependent, as in case A, then determinant must be 0. But here, it doesn't have to be two rows or two columns are the same. Just a dependence is okay. And so this statement is wrong. However, that direction is true. So if you start with here, if two rows or two columns are the same, or a row or a column is 0, then determinant of A is 0. Okay? Okay, this is end of the section. Thank you.